Hi, Dr. Revis here, and in this video I'd like to give a short lecture on how to carry out some simple combustion analysis calculations. Let's do it by working some problems. Problem number 1. A 1.41 gram hydrocarbon sample was burned in air. The products collected were 38.8 grams of carbon dioxide and 31.7 grams of water. What is the empirical formula for the hydrocarbon? Notice we said that it's a hydrocarbon, so we'll assume that it's all carbon and hydrogen. So how do we do this? First, it's important to recognize that carbon dioxide is an indirect indicator of the percent carbon or the mass of carbon in the sample. Water is an indirect indicator of the amount of hydrogen, the mass of hydrogen. Therefore, we will use carbon dioxide to find carbon, and we will use water to find hydrogen by examining their ratios based upon the molecular formula stoichiometry. So let's carry out the dimensional analysis, starting with the given 38.8 grams carbon dioxide. We then use a conversion factor where 44.0 gram carbon dioxide is in the denominator and 1 mole of carbon dioxide is in the numerator. This is a standard dimensional analysis conversion. Next, we convert the moles of carbon dioxide to moles of carbon through the ratio of carbon in carbon dioxide, which is 1 mole of carbon per every 1 mole of carbon dioxide, as shown here. We do the calculations and we obtain 0.882 grams of carbon. Next, we convert the grams of water to moles of hydrogen by using a dimensional analysis with 18.0 grams water in the denominator, 1 mole of water in the numerator. Then we convert to moles of hydrogen by dimensional analysis with 1 mole of water per every 2 moles of hydrogen. The 2 moles of hydrogen came from the molecular formula H2O. We do the calculations and we obtain 3.52 moles of hydrogen. We then take the smaller of the values and divide it into the larger one, and we obtain 1 mole of carbon and 4 moles of hydrogen for an empirical formula of C1H4. It is important to note that the molar ratio used to convert carbon dioxide to carbon will always be 1 mole carbon per 1 mole of carbon dioxide. The ratio used to convert water to hydrogen will always be 2 moles hydrogen per 1 mole of water. Let's continue our practice. Problem number 2. Same problem. A 1.41 gram hydrocarbon sample was burned in air. The product collected was 38.8 grams of CO2 and 31.7 grams of water. In this case, we want to find how many grams of carbon and how many grams of hydrogen were produced. This problem is also worked using dimensional analysis. And in fact, the first main step in this dimensional analysis has already been carried out, where we convert to moles of carbon and moles of hydrogen. Therefore, we need only to extend this by converting the moles of carbon to grams of carbon using the molar mass of carbon at 12.0 gram per mole, and we convert the moles of hydrogen to grams of hydrogen using the molar ratio of hydrogen of 1 gram per 1 mole, and we obtain 10.6 grams of carbon and 3.52 grams of hydrogen. Let's try a third problem. And actually, it's the same problem again. However, in this case, we want to find out how many moles of oxygen were used. It's important to note that the amount of oxygen consumed equals the amount of oxygen that shows up in the carbon dioxide and the water. In other words, the quantity of oxygen consumed is proportional to the amount of oxygen formed in carbon dioxide and water. So therefore, we will do a dimensional analysis where we convert grams of carbon dioxide to moles of oxygen. And in this case, we do the first unit conversion using gram per mole, or the inverse of gram per mole for carbon dioxide, times the molar ratio of oxygen in carbon dioxide, which is 2 moles of oxygen per every 1 mole of carbon dioxide. We obtain 1.76 moles of oxygen. We do likewise when we use water. We start with 31.7 grams of water. We convert it using the inverse of the molar mass, grams on the bottom, moles of water on the top, and then we convert the moles of water to moles of oxygen, which is 1 mole per 1 water. In other words, there is 1 mole of oxygen in 1 mole of water. In the case of carbon dioxide, there are 2 moles of oxygen in 1 mole of carbon dioxide. When we run the calculations for the moles of oxygen in water, we obtain also, coincidentally, 1.76 moles of oxygen. When we add these together, we get 3.52 moles of molecular oxygen in the final composition. That 3.52 moles of molecular oxygen is converted to diatomic oxygen using the conversion factor of 1 mole of O2 per every 2 moles of oxygen to give us 1.76 moles of diatomic oxygen. So in this reaction, 1.76 moles of oxygen from the air was consumed. Let's work another problem, problem number 4. In this case, we want to know how many grams of methane were consumed in this reaction. You may recall that we found the empirical formula was CH4, which is the formula for methane. So we can write a balanced equation for the reaction of methane plus oxygen, and we show that here, where you have 1 mole of methane plus 2 moles of diatomic oxygen to give carbon dioxide plus 2 moles of water. So the question is, how many grams of methane were consumed? We can find that answer by carrying out a dimensional analysis based upon the 1.76 moles of oxygen that was consumed times 1 mole of methane over 2 moles of oxygen. We know that that's the proper dimensional analysis since the oxygen shows up in the denominator. We then convert that further to the grams of methane, and we get 28.2 grams of methane. In this problem, we essentially converted the moles of oxygen to moles of methane, and then we found the grams of methane. Let's work one more problem. A 1.005 gram of an alcohol composed of CH and O was combusted to produce 2.829 grams of carbon dioxide and 1.159 grams of water. What is the empirical formula? The first step here is to find the moles of carbon and hydrogen because we have indirect indicators of what that mass might be based upon carbon dioxide and water. So we carry out a dimensional analysis of the 2.829 grams of carbon dioxide using the inverse of the molar mass. We then convert the moles of carbon dioxide to moles of carbon to obtain 0.06430 moles of carbon. We carry out a similar dimensional analysis for water. We carry it through using the inverse of the molar mass times the ratio of the moles of hydrogen per moles of water, which is 2 to 1, and we obtain 0.1288 moles of hydrogen. Now that we have the moles of carbon and hydrogen, we can use those values to obtain the mass of hydrogen and carbon and use that value to find the grams of oxygen. And we show you how we do that here. We take the moles of carbon and we convert it to grams using the molar mass of 12.0 gram per mole. using a dimensional analysis format, and we obtain 0.7716 grams of carbon. We do likewise for hydrogen using 0.1288 moles of hydrogen and the molar mass by a dimensional analysis, and we obtain 0.1288 grams of hydrogen. The carbon plus hydrogen adds up to 0.9004 grams. Well, since we know that the original mass of the sample was 1.005 and we only have carbon, hydrogen, and oxygen, we can subtract the mass of carbon and hydrogen to obtain the mass of oxygen. And when we do that, we obtain 0.1046 grams of oxygen. Next, we'll take those grams of oxygen. We will carry out a dimensional analysis with the inverse of the molar mass using grams oxygen on the bottom and moles oxygen on the top to give us 0.006538 moles of molecular oxygen. It's very important when carrying out these calculations that you differentiate between diatomic oxygen, which is the reactant taken from the air, and monoatomic oxygen, which is the form of oxygen consumed in the products or the compounds. Now that we have the moles of carbon, hydrogen, and oxygen, we can use the ratios of the larger value to the smallest value, and we find in this case for carbon we get a value of 10. In the case of hydrogen, we get a value of 20. In the case of oxygen, which was the smallest molar ratio, we obtain a value of 1. Therefore, our empirical formula for this alcohol is C10H20O1. So there you have it, a short lecture on how to carry out some simple combustion analysis calculations.